So this is Gubbi online classes for Ncert 10th standard and Cbse 10th standard for mathematics and science. So welcome back to light. So in the previous session of light we had discussed regarding the refraction, the very important concept of refraction. So whenever light ray travels from one medium to another medium, that is where there is a difference in optical density, then we can see the light ray bends either towards the normal or away from the normal. That is depending upon from which medium to which medium the light ray is traveling. So case 1, if the light ray is traveling from optically rarer medium into an optically denser medium, then the light ray bends towards the normal. So in the second case, if the light ray is traveling from a denser medium into a rarer medium, then the light ray bends away from the normal. So these two phenomena taken together, it's totally called refraction. So why the light ray bends? That was the question we discussed in the last class. So here the light ray bends because of there is a change in the speed of light when it travels from one medium to another medium. So if the light ray enters from a rarer medium into a denser medium, the speed of the light decreases. So here denser medium, in the sense, it doesn't mean that the density of the medium is more. It's not like that. It should be not considered like that, because density of water and kerosene, when you compare, density of kerosene is less than that of the water. So something like that. So light ray, the speed of the light ray decreases as it enters into the that is denser, optically denser medium. So optically denser medium and density of substance, maybe they are not related to each other. So when the light ray enters from a denser medium into a rarer medium, the speed of the light suddenly increases. So this makes the light ray to bend away from the normal. So this making an angle, that is angle of incidence and angle of refraction, totally different from one another. So this phenomenon of light, the bending of light when it travels from one medium to another medium, is called refraction of light. So in last class we had discussed all these things. So in today's class we will be going with a very important topic, that is refraction of light through a rectangular glass slab. Refraction of light through a rectangular glass slab. So when the light is meant to fall on a rectangular glass slab, let's see what happens, what is the phenomenon happening inside. As we have taken a rectangular glass slab, light enters into the rectangular glass slab, that is from rarer to denser, and after the light traveling inside the rectangular glass slab, that is denser medium, it goes out into the air again. So let's see what happens there. So maybe in the last class, particular picture what I showed you in that is on the board. So it had different medias where the light ray was traveling. I hope we got an idea. So out of that we are going to take only the rectangular glass slab and see how the light behaves. Right. So refraction through a rectangular glass slab. So this is our topic today, right? So let us take a rectangular glass slab here. So this is the rectangular glass slab. For our convenience, let us name it. Let us call it as AB and CD. So here AB and CD are the parallel sides of the rectangular glass slab. So this side is parallel to this and this side is parallel to this. Okay. Now let us consider a light ray falling obliquely in the sense not at perpendicular to the mirror. It is obliquely falling on the face of the mirror. So when it falls at this point, that is the interface between the air and glass. So this is, you can call it as air, and this is glass, and again it is air. So here the light ray is now traveling in air and it meets the surface AB of the rectangular glass slab, that is the line AB is the interface between the air and glass. So as the light ray is incident at this point, so it is the light ray is traveling from a rarer medium into an optically denser medium. It is optically rarer medium into an optically denser medium. So to analyze the change in the angle, we will draw the normal at this point. So the light ray is going to bend towards the normal because the light ray is traveling from an optically rarer medium into a denser medium. So let us call it as, that is, let us call it as this as angle I, that is angle of incidence, and let us call this as the angle of refraction. Right, this is the angle of refraction. So here, angle of incidence and angle of refraction are totally different here because the light ray is traveling from one medium to another medium. So now the light ray after refraction is traveling in the same medium, that is glass. So no refraction takes place until it hits the another interface which is separating the glass and air. So that is CD. So at this point, the light ray is traveling from a denser medium into a rarer medium. So let us draw a normal at this point to analyze the reflected light ray. So here the light ray is now that is, as it is traveling from an optically denser medium into an optically rarer medium, bends away from the normal, little bit away from the normal. So this is the angle of refraction, that is okay R1, and this is the angle of incidence, that is okay, let us take it as I1. So here at two places the refraction is going to take place. One, while the light is entering from an optically rarer medium into a denser medium, and another point when the light ray enters from a denser medium into a rarer medium. So here at these 2 points, maybe you can call it as N and M. So at these 2 points on the interfaces, we can see that the refraction is happening. So when we draw this light ray, that is the incident light ray, in a straight line path, when we draw this straight line, that is incident light ray, here we can see that these 2 light rays are exactly parallel to each other. That is the refracted, that is emergent light ray, and the incident light ray which is extended, they are exactly parallel to each other. So why they are parallel to each other, that's very important. So here the angle by which at the surface AB the light ray bends towards the normal is equal and opposite to the angle of this refracted light ray which bends now that is away from the normal. So this angle will be equal to this. So these angles are both equal and opposite. One angle, as the light ray bends here, that much of angle is seen here which bends away. But however, there is a sideways lateral shift. That is, the light ray it has to pass like this, but we can see a shift here. So this happens, right? So why the emergent light ray, that is we can call it as some MP, we can call it as ON. So ON is the incident light ray and MP is the emergent light ray. So this emergent light ray and the incident light ray, they are exactly parallel to each other, and we can see the shifting of the light ray from this position to here. So this is called as the lateral shift. So why this lateral shift happens? Because here the angle of incidence here, that is angle of refraction at the point that is the interface AB, and the point and the angle of refraction at the interface DC are equal and opposite. So this is the emergent light ray and this is the incident light ray, and we can see this lateral shift. So this is how the refraction takes place through a rectangular glass slab. Right. So we'll go with the next concept. So it will be asked for 2 marks for you. So we'll go with the next concept, that is loss of refraction. Loss of refraction. Right. So here loss of refraction, very important, will be asked for 2 marks for you. Both are very important laws. So whenever the refraction takes place, whenever the light ray travels from one medium to another medium, refraction happens. So here the incident light ray, this is the refracted light ray. So this is the refracted light ray, the incident light ray, the refracted light ray, and the normal at the interface separating the 2 media at the point of incidence, they all lie on the same plane. This is the first law of refraction. You have to remember this, right? The incident light ray, the refracted light ray, and the normal at the interface separating the 2 media at the point of incidence all lie on the same plane. So that is the first law of refraction. That is, the the light ray which falls on this rectangular glass slab, the light ray after refraction doesn't come out like this or go inside the board or go something like this. It doesn't happen. Just like in the laws of reflection, what you have seen, the same thing happens here also, right? But the angle of incidence will not be equal to angle of refraction. That is, you have to remember. Angle of incidence will be equal to angle of reflection. That happens. But here, where does it happen? So once again, the incident ray, the refracted ray and the normal at the interface separating the two media at the point of incidence all lie on the same plane. So this is the first law of refraction, right? So first law. So the incident ray, the reflected ray and the normal all lie on the same plane in simple words. In simple words you can do it like that, right? So let us go with the second law, which is very, very important. So the second law is also known as Snell's law. The second law is also known as the Snell's law. Very important. Now, here, the sine of angle of incidence, the ratio between the sine of angle of incidence to the sine of angle of refraction is always a constant for a given color of light and for the given two media, that is with respect to the given two media. So that is what we call the second law of refraction, that is called as Snell's law. So Snell's law is also called the second law of refraction. Second law of refraction is called Snell's law. So very simple. The sine of angle of incidence. Sine, that's a trigonometric ratio where you are going to learn it in your mathematics class, where your teacher is going to teach you that. So sine of angle of incidence, the ratio between the sine of angle of incidence, that is what we do is we do a construction here, we take it as 90 degrees. So here we take this as 90 degrees here, we apply trigonometric ratios and find out the sine I and sine R, and we do some mathematical things which is not required for you now at present. So just you can, if you follow this itself. The sine of angle of incidence to the sine of angle of refraction, that is sine of angle of incidence to the sine of angle of refraction, is always a constant for a given color of light and for the given two media, that is for the given two media, right? So this is symbolically or mathematically written as sin I by sin R, that is sine of angle of incidence and sine of angle of refraction, that is sine 45 degrees, sine 30 degrees, sine 25 degrees, sine something like that, right? So when you take the ratio between the sine of angle of incidence and sine of angle of refraction, that will be equal to a constant. That's equal to a constant. So this is the second law of refraction, that is called as Snell's law. So once again I will repeat, the sine of angle of incidence to the sine of angle of refraction, that is the ratio. So that ratio will be equal to a constant, right? And this is true for a given color of light, because light has different colors. Light has different colors. If you put yellow light, the sin I by sin R constant will be something. If you put some red light, sin I by sin R constant will be some other value. So if you put some other light, color light, because every light, color of light have different wavelength and different frequencies. So depending upon the wavelength of the light coming inside, sin I by sin R constant will be decided. So and also it depends on, that is the medium which you are using, the two media. So here I am using air and glass. So it depends on the medium also which you are using. So sin I by sin R is a constant. So the sine of angle of incidence to the sine of angle of refraction is always a constant, right, for a given color of light and for the given two medias. So what is this constant? Sin I by sin R is called, I told you this is a constant. So what is that constant called? This constant is called as the refractive index. It's called as refractive index. So it's a very important word. You have to listen to me very, very carefully now, because I am passing through a very delicate part of optics, that is ray optics. So this constant is called as the refractive index. Now, what is this refractive index? So here, refractive index is for a medium. Is for a medium. That is, we compare the speed of light in this medium, that is medium 1, and the speed of light in this medium, and the refractive index is of this medium, that is second medium with respect to the first medium. Right? That is how you have to understand. That is how it comes. Right? Concentrate. So constant, that is called refractive index. For example, I will take this. Refractive index is indicated by the letter N, and it has no units. It doesn't have any units, so it is represented by N. Okay. Here I have okay, I will go like this. Speed of light N A by speed of light in water. So, the refractive index is the ratio between the speed of light in air to the speed of light in water. So, in this example, I have taken glass. Okay, I will take glass section. So, now, here N represents the refractive index. Refractive index of a medium is the speed of light in air by speed of light in glass. That is, here N represents the refractive index, which is the speed of light in glass. That is the refractive index of glass. Refractive index of glass is equal to speed of light in air by speed of light in glass. That is, here I can write G. Refractive index of glass is given is equal to the ratio of speed of light in air by speed of light in glass. That is refractive index of glass. For example, I will take another example. Here is some medium. So this is first medium and this is second medium. The light travels from the first medium, gets refracted and travels into the second medium. After refraction, it travels into the second medium. So here, the refractive index of, if I represent this second law as Snell's law, refractive index of second medium with respect to first medium. This is how it is written. Refractive index of second medium with respect to first medium is equal to speed of light in medium 2 by speed of light in medium 1. So, refractive index of medium 2 with respect to medium 1 means the speed of light in medium 2 by the speed of light in medium 1. The ratio. So, here what happens is, here the speed of light is something. Inside, as it comes into the second medium, the speed of light becomes something else. So, here it changes. The speed of the light changes. So, when compared to the first medium, the speed of light in the second medium is the refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium is defined as speed of light in medium 2 by speed of light in medium 1. Okay, I will interchange. If I do N12, then it is speed of light. Speed of light in medium 1 by speed of light in medium 2. So, refractive index of medium 1 with respect to medium 2 is the speed of light in medium 1 by the speed of light in medium, that is speed of light in medium 2. So, this is the refractive index of the medium. So, here, what is the change in speed? Whenever the light ray enters from one medium to another medium, what amount of speed is changed when it enters in the second medium is the refractive index of this medium. So, whenever the light ray enters from one medium to another medium, what amount of speed changes in this medium is the refractive index of this medium with respect to this. That's called refractive index. So, this is indicated by like this. So, speed of light in that is speed of light, that is refractive index of medium 2 with respect to medium 1 is the speed of light in medium that is, sorry, let us take it as 1. Speed of light in medium 1 by speed of light in medium 2. So, that is the speed of light in medium 1 is different, speed of light in medium 2 is different. So if you want the speed of light in medium 2, that is refractive index of medium 2 with respect to medium 1, can be written as speed of light in medium 1 by speed of light in medium 2. So here it changes. Refractive index of medium 1 with medium 2 is the speed of light in medium 2 with respect to the speed of light in medium 1. So this is what we call relative refractive index or just refractive index. Relative refractive index or just refractive index, both are same. So here we go with another concept, that is absolute refractive index. This is very important. Absolute refractive index. Absolute refractive index. So what is this? It is slightly different. It's simple but slightly different. Right, you can see here. Speed of refractive index is represented by n. N is equal to speed of light in, for example, vacuum. You can take vacuum or air, whatever you want. So speed of light in vacuum by speed of light in, for example, glass. For example, I have taken glass. So here speed of light in vacuum is the highest, that is 3 into 10 to the power 8 meter per second, that is the highest. This is the ratio we are taking with the speed of light in glass. So when you take the ratio between the speed of light in vacuum to speed of light in glass, then it is called absolute refractive index of glass. It is called absolute refractive index of glass. So here what I have taken, speed of light in medium 1 by speed of light in medium 2. These are two different media, maybe air and water, maybe glass and water, maybe glass and alcohol, or maybe glass and oil, something like that. Here we are not taken air or vacuum. So if you compare the speed of change in speed of light in glass with the speed of light in vacuum, when you take the ratio, then it is called absolute refractive index of glass. So I will give another example. I want absolute refractive index in some ice, absolute refractive index of ice. So I can do like this: speed of light in vacuum or air, whichever you can take, vacuum or air, by speed of light in ice. So when you take this ratio, that gives the absolute refractive index of ice. So n is equal to speed of light in vacuum by speed of light in ice gives absolute refractive index of ice. Speed of light in vacuum by speed of light in glass gives absolute refractive index of glass. Speed of light in vacuum by speed of light in maybe alcohol gives the absolute refractive index of alcohol. Refractive, that is speed of light in, for example, speed of light in glass to speed of light in alcohol is the refractive index of alcohol. That's all. That is relative refractive index of alcohol, not absolute. So if you want absolute, you can go like this. So n is equal to speed of light in vacuum is indicated by C. That is speed of light that is indicated by the symbol C, and speed of light in ice will be always less than this, less than vacuum. So therefore we will take it as V. N is equal to C by V is the formula for this. So what is the formula to calculate absolute refractive index of any medium? That is N is equal to C by V. That is speed of light in vacuum by speed of light in the medium. So that gives the absolute refractive index of medium. So this is how it goes. So you will be given some refractive index of a material, you will be given the speed of light, so you can easily calculate the value, that is the speed of light in this medium. So you will be given speed of light, and you will be given that is the value, the speed of light in particular medium, so we can calculate its refractive index. So more the refractive index of a medium, lesser the speed of light. Less the refractive index of a medium, more the speed of light. So something like that you can consider. Right. So on what factors does the refractive index of a material depends? So the refractive index of a material depends on nature of the medium. Nature of medium. That is, what is the nature? What is the medium made up of? It is air or water or glass or whatever it is. By what material it is made up of? So second one is, that is nature of the medium. That is material of the medium also. That is nature or material we can take. So whether it is glass or a solid or a gas or a liquid, whatever it is. So then it depends on the density of medium. Density of the medium. So then the third point depends on the color of light. Color of light which enters into the medium. So color of light, because every color has different that is wavelength. So therefore it depends also on the color of light. So this is that is refractive index depends on the nature of light, density of light, and color of the density of the medium, nature of the medium, and color of light. Okay. So here we have two refractive index. One is relative refractive index or just refractive index, and another one is absolute refractive index. The speed of light in vacuum to the speed of light in any medium gives the absolute refractive index of that medium. So that is speed of light in medium 1 by speed of light in medium 2 gives the relative refractive index of medium 2, which is in the denominator. So here speed of light in medium 2 by speed of light in medium 1 gives the refractive index of medium 1. Speed of light in medium 1 by speed of light in medium 2 gives the refractive index of medium 2. So it's something like that. So if it is taken with air or vacuum, as I told you here in this case, then it becomes absolute refractive index. Okay, I hope you understood this. So let us go with some refractive indices of different materials. So one by one, and I will tell you how to analyze them. Okay, so these are the refractive indices of different materials. So vacuum, the refractive index is 1. How it is? Speed of light in vacuum by speed of light in vacuum is, it cancels, it's equal to 1. So therefore refractive index is 1. So next is air, it's very less. The refractive index of air is 1.000036. In the sense, light can travel in vacuum when compared to air by 1.0036 times. 36 times, that's the thing. So next is water, its refractive index is 1.30. This means the light can travel 1.30 times faster in vacuum than when compared to water. I hope you understood. Once again I will tell you. Refractive index of water is 1.30. Refractive index of water is 1.30 means the speed, the light can travel 1.30 times more, that is 1.30 times with more speed than when compared to water in vacuum. So in the sense 1.30 times faster than the speed of water in vacuum. So that's the thing. So next is some sugar solution which is 30% concentrated. It is 1.38. So here, what does it mean? The light can travel 1.38 times more faster in vacuum when compared to sugar solution. That's the thing. So once again, glass. So it's 1.5. The refractive index of glass goes on continuously changing depending upon the type of glass. So here it's a typical glass. It's 1.5 refractive index. So it means the light can travel 1.5 times more faster in vacuum when compared to this glass. So here when the air enters from vacuum to this glass, the speed of the light decreases by 1.5 times. Decreases by 1.5 times, something like that. So diamond is 2.4. This is the highest refractive index what we have seen. So here the speed of light in diamond is 2.4 means the light can travel 2.4 times more faster in vacuum than in diamond when compared to diamond. Right? So this is how you have to understand the refractive index. So these are the different refractive indices given. Right? So in tomorrow's class we will be going with some more numericals which are very important on the refractive index. Very important. So I hope you enjoyed the class. It was the most important class. Please read the textbook thoroughly. Everything what I have told you now, what I have discussed in the class today, everything is in the textbook. Please go through that. Right? Please present the homework which I am going to give you, which I have given you in the WhatsApp. Right? Please respond well so that you are on the right track. Right? So stay home, stay safe, keep learning. Thank you.